Hey, welcome back to your favorite fundamentals of college math class. We're going to take a look at probability, an introduction to probability. The probability of an event is the chance or likelihood that it will occur. So, for example, there's three types. Three types. First is subjective probability. This is really just an educated guess. Like for example, somebody will win a game, right? There's going to be so many variables. You might be able to guess that, but it's pretty hard to do it. It's kind of a subjective probability, an educated guess. The second type is an experimental probability. So when a weather reporter says there's 10% chance of rain based on prior evidence, that's an experimental probability. Let me give you another one of that. Let's say you roll, you have a 1 in 2 chance of flipping a heads, right? So let's say you flip a heads 10 times, flip a coin 10 times, right? The experimental probability, maybe you got heads 7 times instead of exactly 5 out of 10. That's experimental probability. Theoretical probability, theoretically, if I flip a coin 10 times, I theoretically should get a heads 5 out of 10 times, right? But it may not have been exactly what happened. So theoretical probability is like the probability of what should occur mathematically, right? Experimental probability is actually what did occur. And maybe I flip it 100 times. And now I flip it 100 times and I get 55 heads. Well, theoretically, I should have got 50 out of 100, right? But as the trials increase, right? And I think there was somebody that actually did this in jail or something once. Some theoretical probability I heard about, somebody writing a book about this. But as the number of trials increases, you will approach your theoretical probability, right? And so when we get into probability and later expected value, you're going to realize, oh, this is why those casinos are multi-billion-dollar buildings, because they have statisticians working for them that make sure that as the number of trials goes to infinity, that the house wins in their games, right? So they're making money. They've guaranteed it with mathematics. Right? That's theoretical probability. All right, let's get into probabilities ranging. They'll range from 0 or 0% up to 100% probability, right? So it'll be a number between, a decimal between 0 and 1. Let's do some examples here. In this course, you guys, we're going to have all our probabilities between 0 and 1. If you're getting a negative or greater than 1, you've made a mistake in this course. Just check your work. So let's do some basic concepts here. A little vocabulary. The result of an experiment is an outcome. An event is any particular outcome, or it could be a group of outcomes. A simple event is just an event that cannot be broken down further. And finally, a sample space is all possible outcomes. Okay. Now, the probability of an event occurring is the number of outcomes corresponding to that. In other words, the number of successes over the total number of outcomes. So let's do just a simple six-sided die. Our sample space, what's our sample space for this? In other words, what are all possible outcomes? Well, we could roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6, right? So describe the sample space, we just did that, and some simple events. So some simple events would be, we could roll a 1, or we could roll whatever we want, right? Whatever, roll a 5, but those are some simple events. We could even do a more complex event. We could roll a number bigger than 4. That could be an event as well. So let's do some actual probabilities. So if we roll a six-sided die, you can see the sample space right there. What's the probability, part A? What's the probability that we roll a 2? Well, how many number 2s are there on the die? 1, right? There's one success, and how many are in our sample space? 6 possible numbers, right? So the probability of rolling a 2 is 1 in 6, or 0.16 repeated. So 16.66666%, right, is the probability of rolling a number 2. How about part B? Probability of rolling a number bigger than 4. So of the 6 numbers, how many are bigger than 4? Yeah, 5 or 6, right? Either one of those is a number bigger than 4. So the probability of rolling a number bigger than 4, there's 2 successes out of, when I roll it one time, there's only 6 possible outcomes. I could roll 1, 2, 3, 4, 5, or 6, right? But a 5 or 6, which is my numerator, that's my win. I get a 5 or a 6. So there's 2 winning numbers out of 6 possible numbers. So the probability of rolling a number bigger than 4 is 1 in 3, or 33.3%, 0.3 repeated. One more with 6-sided die. Probability of rolling an odd number. How many winning odd numbers do we have? 3, right? 1, 3, or 5. So probability of rolling an odd number successes over total outcomes. There's 3 winners, or 1, 3, or 5, and there's 6 possible outcomes, 1, 2, 3, 4, 5, 6. So I got a 50% chance of rolling an odd number. Example 4, we have a bag now. We got this bag. We've got 20 cherries, 20 cherries in here. Let me do it with how many are sweet. Looks like 14 are sweet and 6 that are sour. So it looks like there's 20 total. If we reach in and we pick randomly, again, it has to be random, right? What's the probability that it will be sweet? If I reach in and pick out a sweet, well, how many sweet are there? 14 winners, right? Out of how many total in the bag? 20. Yeah, so I got a 7 out of 10, or 70% probability that I pull out a sweet cherry. Let's do a clock example. Number 5 here, example 5. Some random moment, you look at your clock and note the minutes reading. What's the probability at that random moment that its reading is at the 15th minute? What's the probability on that clock? All right, we've got a clock. Anyways, 15's right there. All right. What's the probability at that moment? Well, I have one winner, the 15th minute, right? Out of how many minutes total? 60 minutes total. So we have a 1 in 60 probability. Part B, though, is asking us what's the probability that it's 15 or less? Or less. Right? How many of those are there? Well, it's less. If I count them all up, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How many of those are there? Less than or equal to, how many of those numbers were there? 16. 16 of those out of 60, because there's 16 winners. 15 or less, right? Both of those will go into 4. So we got 4 out of 15, or 26.6 repeated percent. Right? If you're not familiar with a standard deck of 52 playing cards, you've got 2 of the suits are red, the hearts and the diamonds shown. 2 of them are black, the clubs and the spades, the top 2 rows there. And then you've got 2 through 10, ace, jack, queen, king. Okay, and that makes up your cards. Now the jack, queen, and king are called the face cards, by the way. Okay. So that's a little picture of your cards. So let's compute the probability of randomly drawing one card from a deck and getting an ace. So what's the probability of pulling an ace out. Well, how many winning aces are there? Yeah, good. So we got 4 aces right there. Out of how many total cards? Yeah, so both of those will go into 4. So that's a 1 in 13 probability, or 0.07692300769. So 7.7%, 7.69% chance that you pull out an ace from a standard 52 card deck. How about this one? What's the probability that you pull out a red spade? So I'm looking at spades. Well, where's my here's my diamonds. Here's my clubs, right? Here's my hearts. And here's my spades. What color are spades? Black. Yeah. So are there any red spades? No. So what's the probability of pulling out a red spade? That card does not exist. So how many winners are there? 0. Oops. Out of 52. So the probability is 0, right? In other words, it will not happen. You will not pull out a red spade. This is an impossible event, in other words. Remember, all probabilities are between 0 and 1. 0 means it will not occur. This will not occur. A 100% probability is a probability of 1, right? So like, what's the probability I pull out a red or a black card? Doesn't matter which one. Well, all of them are red or black, right? So it'd be 52 out of 52. That'd be 100% probability that I'd pull out a red or black card. All right, now we're going to do the probability that an event does not happen. An event does not happen. So we know from the last section, if we were figuring out the probability of rolling a 6, that's 1 out of 6, right? We know that probability is rolling a 6. So what would the probability of not rolling a 6 be? Well, how many are not the number 6? We know that there's 5 of them, right? It's 5 out of 6. But we actually have a formula for this because it's not always easy as just this scenario. So we have a formula for the probability in an event not happening. And it's right here. The probability in an event not happening, so for example, probability of not rolling a 6 is 1 minus the probability of actually rolling a 6. So 1 minus the 1/6, 6 over 6 minus 1 over 6 is 5 over 6. So probability of not rolling a 6 is 5 out of 6. So again, that can be useful because sometimes we don't always have all the information we want. So the probability of an event not occurring is 1 minus the probability of the event actually occurring. Okay, so let's do some examples here of a complement. Probability of not pulling a heart. So probability of not pulling a heart. So by the formula, that would be 1 minus the probability of actually pulling a heart. So let's go to the side and figure out probability of pulling a heart. Well, how many hearts do we have? That whole row, right? Looks like there's 13 of those hearts. So probability of rolling a heart is 13 out of 52. In other words, 1 out of 4. 13 out of 52 is the same as 1 out of 4. So let's go back. So that's number 1. Now let's go back to figuring out the probability of not rolling a heart. Probability of not rolling a heart then would be 1 minus 1/4. So I got 4 fourths minus 1/4. I have a 3 in 4 probability of not pulling out a heart. All right, here we've got a jar. It's got 28 marbles total. Looks like 12 of them are red. And if there's 28 total, looks like we don't know what the other ones are. So if there's 28 total, 28 minus 12, 16 are other. Put in capital O for something else. Again, we don't know what the other colors are, right? But it says, what's the probability that you do not pull a red out? Well, it's 1 minus the probability that you do pull a red out, right? So let's go to the side and figure out the probability that you pull a red out. Well, how many reds? If you pull one out, there's 12 winners out of how many total marbles in there? 28, right? Both of those will go into 4, so 3, 7. So the probability you pull a red out is 3 in 7 is your probability. So let's go back over here. The probability that you do not pull a red would be 1 minus the probability that you do pull a red. So we get 7 sevenths minus 3 sevenths. 7 minus 3 all over 7 is 4 sevenths. That's the probability that you do not pull a red out. How about this one here? Your favorite basketball player is an 84% free throw shooter. Find the probability that he does not make his next free throw. Probability he does not make the free throw would be 1 minus probability that he does make the free throw. We know he shoots it at 84%. Make sure that's a decimal, 0.84. So 1 minus 84% or 1 minus 0.84 is 0.16. That's the probability that he misses the free throw based on his percentage. One of my favorite applications of probability concepts is with expected value. Expected value. This is where they can determine insurance policy rates, right? Casino and government agencies, casinos that run gambling operations, lotteries, all this stuff. They definitely understand this, right? And frankly, hope that you don't learn this concept. Why? Because you realize that gambling is not winning formula for financial success in the long run, because they guarantee you that as the number of trials goes to infinity, in other words, the more times you gamble, the more you approach the expected value, meaning the more money you're giving to the casino, right? So, losing formula. Now, what is the expected value? This is how we come up with it. It's the outcome times the probability of the outcome plus the next outcome times the probability of its outcome, and so on. I think it's shown nicely in roulette. So in the casino game of roulette, the wheel has 38 spaces. You can see it shown there. 18 of them are red, 18 of them are black, 2 of them are green, if you're not familiar with roulette. In one possible bet, the player bets $1 on a single number. If that number is spun, they get $36 if they win, right? So they get the original 1 plus the 35. Otherwise, they lose their dollar. On average, how much money should a player expect to win or lose if they play the game repeatedly? So this is an expected value question. We either win times the probability of winning, or we lose times the probability of losing. So let's figure out the expected value of this scenario with roulette. If we win, what did we win? We win $35. Now, what's the probability of winning? You're only betting on one single number, so it's only one number wins out of the 38. That's your probability that you roll that number, okay? Now, to calculate expected value, what do we lose? Well, we're only out, how much did we bet? $1. So we lose, notice I make it negative. I lose $1. Over here I was winning 35, right? I'm losing $1, but I have a much higher probability of losing. Probability of losing, there's 37 losers out of 38, right? 37 losing numbers out of 38. So we can multiply this, so 35 over 38 plus negative 37 over 38. So I got 35 over 38 minus 37 over 38. 35 minus 37, negative 2 over 38, or negative 1 out of 19. So my expected value, negative 1 out of 19, let me put it in decimal form. That's negative 0.05263, or negative 5.3 cents. So what is this saying? So on average, in other words, the more you play, you lose. That's the negative part. You're losing 5.3 cents every time you play. Remember, it's $1 to play. Mathematically, that's what's going wrong, right? This is saying in the long run. Sure, you might do it and lose the $1, or maybe you do it once and you win $35, right? But in the long run, right, the more you play, the more you're approaching the expected value, meaning every time you're losing 5.3 cents. Even though you're periodically winning, even if you played thousands of times, right? You're still losing in the long run. So this is of note, you guys. If the expected value of a game is negative, not a good idea unless you're playing for purely entertainment purposes. And frankly, how are you going to find a positive expected value game? You're probably not, because casinos are not going to do that because they're not making their money, right? They want to have, they've guaranteed that they're going to win, right? Now, if the expected value of a game is 0, that's actually called a fair game, right? It's mathematically fair. Okay. Expected value for casino games is going to be what? Negative. Again, they guarantee, that's how they build those billion-dollar buildings, right? Keep that in mind. Play for entertainment reasons only. Mathematically is pretty stupid otherwise. All right, example 2. A raffle ticket costs $3. There's one winning ticket out of the 150 tickets sold. The winner gets $300. What's the expected value for the player of the raffle ticket? Should he buy a ticket? All right, so we've got this local little raffle or whatever is going on, right? Let's figure out this expected value here. We could lose times the probability of losing, or plus we could win times the probability of winning, right? So let's figure out the expected value. If we lose, how much do we lose? Well, the cost of the raffle ticket. All right, so we're losing $3 if we lose. Now, how many losing tickets are there? Remember, there's only one winning ticket out of 150, so how many losers are there? 149. So pretty likely that you lose, right? Now, if we win, you get $300. Now, it did cost you $3, right? So what are your actual winnings? 300 minus the 3, $297. Yeah, so that's your net winnings, right? Because it did cost you $3 to buy the ticket. Now, the probability of winning is there's only one winning ticket out of the 150. So I multiply negative 3 times 149. I get negative 447 out of 150. 297 times 1, 297 over 150. Negative 447 plus 297. That's negative 150 over 150. So it's negative 1. So the expected value is negative. So this is saying, again, on average, you are losing $1 for every ticket you buy. Again, in the long run, right? That's in the long run. Should you buy a ticket? What's the expected value? Is it positive or negative? negative. I mean, realistically, you shouldn't try. Maybe you're buying it for charity. Who knows? Whatever. But you're expecting to lose because you got negative expected value, right? And they've made it that way so that the raffle makes money. They got to make sure that the raffle makes some money for the charity or whatever it is, right? But on average, right, you buy tickets. You buy all the tickets. Guess what? You still lost money, dollar for every ticket, right? All right, let's do an insurance one now. 40-year-old man in the U.S. has a 0.242% risk of dying during the next year. Okay, an insurance company charges $275 for a life insurance policy and pays out a $100,000 death benefit. What's the expected value for the person buying the insurance? So the expected value would be the person could die times the probability that they die, right? That's one outcome. In the next year, you could die and you get the $100,000. Or you could live times the probability of living, right? Now, if you die, that's kind of like winning, right? Well, not really winning, but losing in a weird winning way. But the $100,000 is there, but it costed you how much for the insurance policy that year? $275. So your net winnings, if you will, is $100,000 minus $275, because again, it costed you $275 for the insurance policy, right? Now, times the probability that you die. What's the probability that you die? 0.242% risk of dying, right? Like 3% would be a 0.03 decimal. So this is 0.00242 as a decimal. 0.00242. So make sure that's as a decimal, right? So that's the outcome if you die. Now, if you live, what do you get? Well, you paid for the insurance policy. So you're out $275. You had to pay for the insurance policy. But you have a much higher chance of living, right? The probability of living, in fact, let me go to the side for a minute. Probability of living is 1 minus the probability of dying. And we know dying is 0.00242. So 1 minus 0.00242 is 0.99758. 0.99758. So I've got 99,725 times 0.00242. I got negative 275 times 0.99758. So we got 241.3345 minus 274.3345. So that ends up being negative 33. That's our expected value. So it's negative, right? Because for people buying insurance, the insurance company has to operate. In other words, they got to have money. They have to have money to pay out on death benefits and obviously meet the salaries and stuff and expenses of the company. So that's why that expected value is negative, right? If they don't have it that way, then they've got big issues as a company financially, right? So there's, and then you're thinking, well, do I even buy insurance? Well, there's obvious benefits to that, right? Like it might be worth the cost. So sure, it's a negative expected value for you. You're losing money year to year, right, in the long run. But it's giving you security. So like a term life insurance is probably a good idea if you're not self-insured, if you don't have enough assets to be self-insured for your family, or maybe you're a single parent and you're a provider for your kids, right? You want to have some sort of term insurance because it guarantees them a death benefit. It guarantees them security if you die young or for whatever reason, right? So that's how insurances work a little bit on a very basic level. Thanks so much for watching. We'll see you next time.